Welcome to the GrainTALK webinar. Today, we have the pleasure of Cam Ogilvie moderating a conversation of rotation impacts on soil health and biology. What a great topic to understand what the impacts are on soil health. With Cam today will be Dr. Laura Vineyard, Dr. Carrie Dunfield, and Dan Petker. Welcome, everyone.
Hey.
Hi.
Thanks.
Thanks again, Marty, for the intro. My name's Cameron Ogilvie. I'm the Knowledge Mobilization Coordinator for Soils at Guelph, which is an initiative of the University of Guelph to promote sustainable soil management in Ontario by connecting researchers, farmers, and farm advisors. I want to start off just by saying thank you to Grain Farmers of Ontario for the opportunity to host this webinar. We get to celebrate something special in this. This is the 40th and the 25th anniversary of the Elora and Ridgetown long-term crop rotation and tillage experiments. So there's 65 combined years of agronomic research in 2 Ontario growing environments. And so as our industry is having conversations about the sustainability of agriculture, these 2 trials offer some really neat research insights into agricultural sustainability. Want to acknowledge a few groups as well. The Elora Crops Research Center and the Ridgetown campus are 2 of 15 research stations owned by the Agricultural Research Institute of Ontario and managed by the University of Guelph through the Ontario Agri-Food Innovation Alliance, which is a collaboration between the Ontario government and the University of Guelph. And so this research is funded in part by the Ontario Ministry of Agriculture, Food and Rural Affairs through the Ontario Agri-Food Innovation Alliance, as well as through Grain Farmers of Ontario and a number of other groups that have supported and funded this research. I am joined today by Dr. Laura Vineyard, who is a professor of sustainable soil management at the University of Guelph Ridgetown campus. She's a co-executive director for Soils at Guelph and a research program director for the Ontario Agri-Food Innovation Alliance. She was named one of the top women in Canadian ag in 2020 for her research on soil health, cover crops, and nitrogen and carbon cycling. I'm also joined by Dr. Carrie Dunfield, who is the Canada Research Chair in Environmental Microbiology of Agri-Ecosystems, another co-executive director for Soils at Guelph, and she's one of Canada's premier scientists working at the intersection of microbiology, ecology, and soil science. And last but not least, Dan Petker is a farmer and a CCA in Norfolk County, a director for the Innovative Farmers Association of Ontario, and a pioneer rep serving with West Norfolk and East Elgin since 1972. He's known for his no-nonsense take on balancing farm economics, agronomy, and soil health. Thanks, everybody, for joining me.
Thanks, Cam.
Thanks, Cam. Thanks.
So this is part 2 of 2 webinars. And in the first webinar, we were really looking at just generally rotation impacts at these 2 long-term trials. I'm going to show the trials on my screen here. But so we were looking at the rotation impacts on yield, primarily yield and yield stability. And so following up on these things, we didn't really kind of get to the question of diving into what's happening, like what's causing this. And particularly it has to do with things that are happening in the soil. And Laura, I'm kind of anticipating that the first question on everybody's mind is, how have these crop rotations affected soil organic matter? So there's a slide with some data here. Can you walk us through what's been the impact on soil organic matter?
Yeah, absolutely, Cam. So this data comes from Ridgetown. At the time of sampling, the plots had been in there for 11 years. So this was sampled in 2006. So we have to keep that in mind. But what we've seen here with this data and similar data at Elora, and we're sampling now to look at how things have changed since 2006 to now. But this slide shows it all in terms of soil organic carbon, more with winter wheat and the rotation. And when I say soil organic carbon, that's organic matter, right? That's when we think of organic matter, that's what you get on your soil test. That's the living and dead, decaying matter. And in this case, we only measure the element carbon, but essentially we can say organic matter. And what we see here is the greater the frequency of winter wheat in the rotation, the greater the soil organic matter, soil organic carbon. And so if we have a soybean wheat rotation, it actually protects against losses of carbon with tillage. So we see a general trend of lower soil organic carbon in, now this is largely surface, right? But we see that with tillage, you tend to have lower soil organic matter, soil carbon, but it depends on the rotation. So, and the other most notable thing is continuous soybeans, very hard on your soil, very low organic matter, and that's because you have very low inputs of plant material, right? Think of your soybean plant. Breaks down high in nitrogen, breaks down quickly, doesn't leave a lot of residues, doesn't input a lot of carbon into your system. And
Right.
so that's what we're seeing here.
And so growing wheat in the rotation, of course, opens up opportunities for cover crops, particularly red clover. Dan, I know you're a big red clover fan. As you look at this data here in terms of carbon, does this match with what your experience has been with your soil health as you're growing wheat and you're growing red clover as well? And what's the value of that?
Yeah, very much so. And we typically farm on soils that have like baseline organic matters of 1.5 to 2.5. And anywhere where we've had long-term wheat and then wheat with red clover, we see these numbers go up to 3, 3.5, and we're stabilizing right around that 3, 4 point. With all the benefits of that come much greater yields.
Right, right. So,
and in Norfolk County, sorry, Cam, and in Norfolk County, you're on sand, right?
Yeah, so we're on sand, loamy sands. Like it's even just growing a small grain just helps everything go. So if you're on the sharp sands, we grow rye. If you're on like the silty loams or that sort of thing, we grow wheat. But a small grain makes everything just kind of work better the longer you have them in the rotation.
Yeah.
And Laura, like we're going to get into, I'm going to jump to Carrie in a little bit to hear about some of the biology impacts, but what is it about small grains? What is it about wheat? What's it about rye that is making the difference?
I wish we do. And, and lots of scientists around the world are observing this effect of having small grains in the rotation. So work out of the Midwest where they have these long-term trials that actually include winter wheat, they're seeing it, well, winter wheat, small grains. And there's lots of work going on. My sense is that we're growing on a different time scale, right? So you're planting in the fall, you have a living crop in for much longer. With that living crop, you're having root exudates and root inputs of carbon. That carbon inputs from the roots is supporting microbial communities, which Carrie will be talking about. And then you have an opportunity for planting a cover crop, which, as you might know, is my area of research.
Right. Okay, so we're looking at the impacts on organic matter. We know that there's impacts on yield. We talked about that last time, and we'll get back to that at the end. Carrie, can you? I'm going to throw up another slide here. This is some of the research that one of your graduate students has done. And so I'd love to hear from you. Both help us understand what these figures are showing us, but then also talk about what's been the rotation impact on microbial communities.
Okay, sure. So come on, you can't understand what those mean.
Circles and
So yeah, so Cam, so what we were really excited to do, one of the questions that has come out when you look at all this data, organic matter changes, and sometimes you see yield changes in these long-term trials. And so one of the things we were really excited to do is look at the microbial communities and just wonder if the microbial communities were changing like we would kind of think that they would be. So these slides are just called principal component plots. So what basically every colorful point on those slides are just basically a soil sample that we took from the long-term trials at Elora. And we took those soils and we brought it back to the lab. We did a DNA extraction and sequencing, and we got a genetic profile. So we look at kind of who's in the community. So on the so either fungal communities or bacterial communities. And so basically the closer 2 points are on that plot, the more similar those communities look. And so we were kind of expecting what we see in the fungal diversity plots, where if you look at each of those colors is a different rotation, and then the open circles are the no-till and the closed circles are the till. So you have very different microbial communities associated with the tillage plots and the no-till plots. And I think this is something we've seen with fungi. We kind of expect that. You also see those little crosses at the bottom. Those are the alfalfa, and they're really sticking out. So the microbial communities associated with alfalfa are quite different. But what we also see very clearly is that each of those rotations also has a really unique microbial community. So going from kind of the bottom to the top of the graph, following the colors, you go from the corn alfalfa rotation and across all rotations. So each of those rotations has a really unique community. And what was really cool about this was we would kind of expect that if we were sampling, say, in the 4th year of the rotation after a really different, so where everything was growing a different crop, but this is actually in the 2nd year of corn. So we sampled after 2 years of corn. So all of these plots, if you look at them, all had corn on them. And you see the microbial communities are really, really different. So the fungal stuff you kind of expect, the bacterial stuff, we actually also see the differences are not as clear, but you do definitely see differences between the till, which are the solid colors, and the no-till. And we also do see significant differences between the rotations for bacteria. They're not as pronounced, but we have some kind of significant community differences within that. So we were pretty excited about it. It's pretty cool to see these communities changing.
And this is in bulk soil? Sorry, Cam.
Yeah, this is bulk soil. This isn't, this is bulk soil. So we went across those plots. We sampled in October, so just after harvest. And we went, randomly across the plots and sampled bulk soil.
And when you say bulk soil, you're distinguishing that from rhizosphere soil?
Yeah,
or soil
from the
around the
rhizosphere.
roots?
So yeah, that's actually something we're looking at this year in the Ridgetown plots. So not stuff that's associated with the roots, but actually within those plots. So the soil kind of between the plants. We go mid-row between corn and then closer to where the plants were. So
right. Okay.
Just a comment on these things. I guess I go from a farm and experience perspective. Like I love these charts, and some people will think that, or may deduce that, like the lower parts of this graph, let's say the lower left quadrants, are bad, but they're not.
Oh, right. No.
And same with like where the alfalfa, like the pure alfalfa rotation is on its own little thing. What's happening in the soil is like everything we do always selects for a result. So this continuous crop rotation of alfalfa, for example, is we're selecting biology, be it fungal and bacterial, to behave a certain way because we're giving it a certain input. Like I see either the continuous corn rotation on here. We have a neighbor, he's been continuous soybeans for 21 years now. most people would say that's a horrifying thing. He has 0 white mold, 0 SDS. He rotates, now that we have like different sources of soybean cyst nematode resistance, he rotates that now, and his yields have stabilized about 12, 13 years ago, and he just sits at 50 bushel beans all the time. And when I look at this chart and I look at the alfalfa one, because that stands out so severely, is like he has selected his field and his biology to become soybean producing land. And it's really amazing to see, like, it's really cool what we can do to the soil life by our management and our inputs.
Yeah, that's one actually thing that we're thinking a lot about is like, can we promote soil biology based on what rotations we're growing, or what cultivars you decide to put in there. So.
Right, because diversity on its own, from a production standpoint, doesn't matter. So long as it has to be functional diversity, and give us resiliency within that. And sometimes we hear or read things that just show all we have to do is always chase diverse. Well, that's great, but we're also in a business, and that diversity has to do something for us.
Right.
And sorry, Dan, would that be in a no-till situation? No-till beans?
Nope.
Soybeans?
No, his cover crop is chickweed. Yeah. And he lets the chickweed grow all winter. And when he kills the chickweed 2 days before he plants his field, and it's tandem disc, 2 passes, and then 1 pass with the cultivator ahead of the planter. It's absolutely everything wrong in what we think, but it's working. And that is a sandy loam soil. Like, he has some forgiveness with like the organic matter and the CEC part, but it's really astounding.
So maybe to jump on the question or the point that you made there, Dan, about function, Carrie, can you, like, have you been able to look into these communities and like, what are the functions that are being selected for in these different rotations?
Right. So that's something that we're really interested in, because I think you guys made a good point. This data just shows that these communities are different, and it actually doesn't even show whether it's more diverse or less diverse. We don't actually, across the board in these plots, there's very little difference in total diversity. We just know that the organisms that are there are different. So it's not, they all have about the same level of diversity, but this graph shows that different organisms are making up that diversity. So like Dan said, our question is really then, how does function of these organisms change? Because there's different organisms and they all have different roles in the soil. So are we seeing a difference in function? And we're getting into that with the whole trial with Edalora and some of the whole trial at Ridgetown, but we did kind of select a couple of plots just for comparison to look at, like, nitrogen cycling. I don't know if we're gonna get to that yet, or
yeah, that'd be great.
What we see is that we have differences. Here we go. Differences in nitrogen cycling between some of these plots. So this was just kind of one of the first passes at looking at function in the LoRa plots, and this is working with Claudia Wagner-Riddle, who looks at greenhouse gas emissions. And so what we were really interested in was how does diversifying your rotation change your greenhouse gas emissions? And our interest was, how do the microbes drive those changes? And so this was kind of a first study in the spring, right after fertilizer was applied. We just followed 2 of the rotations and looked at N2O emissions. So this was comparing a corn soybean rotation to a corn soy wheat with red clover. And what we see is that a couple things. There's higher nitrogen in the corn soy wheat. There's higher moisture at the time that we sampled, and there was actually a higher nitrous oxide emissions at that time point too. So over that period of time, they saw higher N2O.
Right, and all those things kind of come together to produce the higher nitrous oxide emissions.
That's right. Yeah. And we looked at the microbial communities in those plots, and we see the microbial communities are very different. So they're in the corn soy wheat with red clover. there's a lot more nitrogen cycling community. So you see like kind of a tighter nitrogen cycle in those plots. And so that's what's causing kind of that nitrogen turnover really quickly, and suggesting that there's probably excess nitrogen in those plots. They're getting the same amount of nitrogen fertilizer because of the field trial. There isn't a nitrogen credit. So when there's extra nitrogen, it's just being lost as N2O, I think.
Right. Let's get into that point a little bit more, because I think, like, as we look at this, we see increased N2O emissions and we think, oh, that's bad. So the diverse rotation is bad for greenhouse gases. But there's...
Yeah, I mean, we were sad to see that too at first. Trust me, research doesn't always come how you want it to look, but yeah. So one of the things you have to remember in these long-term trials, one of the things that we do in research trials, because we can control things that we can't control, you know, if you're growing, if you care about profitability, is that we put the same amount of nitrogen down on, so Building puts the same nitrogen fertilizer rate across the board, across all these trials, all these rotations. And so in that case, there's actually, we're able to know that it's, what is driving this. In this case, we know it's, there's higher N2O if you put higher amounts of nitrogen than you need.
Right.
But probably it also indicates that what it's indicating is that there's excess nitrogen. And
so Dan, like, as you're advising and as you're managing your own operation, like, you don't apply the same rate of nitrogen when you're in a corn, soy, wheat rotation with red clover. So in essence, this is supporting the benefit of wheat and red clover in the rotation for the nitrogen credit that you get. Is that how you'd look at it?
No, it's actually, I ignore the N credit from clover completely from an economic standpoint.
Okay.
UAN, like 28% and 32%, while like my total expense is high, it's a low cost input. Like for me to go and add an extra 5 gallon of product, it's not a huge deal, so long as commodity prices match, of course. But let's say clover costs me $2 a pound, and I go put on about 12 pounds of clover on, so there's 24 bucks. Costs me $5 an acre to put it on, so there's $29 of N credit. UAN the last couple of years has been so cheap that I can't get that 29 bucks back from the credit that clover actually gives me, so I ignore it. So that the decaying residue and the nodules that drop and shed from my clover, that's for the soil life. That's just there to feed things over the winter, have it there available, and then we just come back and plant corn, act as if it was never there. So.
And the soil life is loving it because that's what's happening.
Like they are starved for, like, that's the whole amazing thing about commercial agriculture or like commoditized agriculture, is we live in a world where nitrogen is like, everything's starved for it. So anytime we can add it and supply it where there's never been, or it's always in demand but low supply, things blossom and bloom. So why not leave it there? Like, I don't have to harvest all of that. So we let the clover be there for the soil life. That's what it's there for. Keeps my ground covered and weed suppressed, but the N credit is there for the soil.
So now, Dan, maybe I think you also don't, you manage your system uniquely to also offset like nitrogen losses from the system. Like, cause you're planting cover crops and things like that in order to prevent losses. Because if you're always just putting stuff into the system, then you run into excess emissions and you run into leaching and stuff.
Right. I guess like we do manage like the losses, like, and our biggest losses are surface soil erosion. So if I keep everything there, it gives it more time for the N to get tied into different structures of biology or into plant roots. And then it's also, if there's active biology and active plant roots, that mitigates a lot of our are kind of our leaching down into the soil, into the water profile below us. And on the sandier soils, like that is crucial. We don't have organic matter to tie things up or CEC to tie things up. So if you have roots and living things that want to eat it and hold it, then when they die, then we can use it instead of it going into the river or to the creek or the lake.
Right.
That's kind of a good point, Cam, because this is on a Laura soil, so that's more of a loam. So one of the things we noticed in the spring was that where the wheat and red clover, that trial was a lot more wet. So if you see like panel B, there's a lot more water being held, and so that might not happen if you're on a sandier, like you might have that draining off more. The other thing to note is like this is the nitrogen. We were measuring microbial communities right over where we side dress nitrogen, and so this is the N2O emission, kind of maximum emissions on that plot because we measured it right over the nitrogen side dress. So we wanted to know exactly what was happening with the microbes. And so if you take that data and expand it over like the whole field, so there's a lot of soil that didn't get nitrogen, then those numbers come down. There's still a difference. It's higher still with the red clover, but it's not as drastic.
Severe, yeah.
Yeah.
Laura, you've also got some soil data that kind of connects to this. You did some, you used some soil health tests at Ridgetown.
Yeah.
Could you talk about these tests that you used?
Sure. So we did it at Ridgetown and also at Elora. So this is Solvita and Slan. They're commercially available soil health indicators. So they're a 24-hour incubation, and you have the soil that's moistened. You seal it in a jar with a color paddle, and just like a pH stick where the color changes with the pH. Same thing when the soil's active, it's releasing carbon dioxide, and in this case we're also measuring ammonia emissions, and so there's color reaction, and then you use a digital reader to measure the evolved carbon dioxide and the evolved ammonia. And what we saw with these soil health indicators is more activity with alfalfa in the rotation, so that permanent cover, and more activity with cover crops than winter wheat in rotation. So red clover with winter wheat or red clover with barley and oats, so the small grains. Yeah, so this is kind of getting back to what Carrie was talking about in terms of function and soil carbon and nitrogen cycling. We see more activity with alfalfa in the rotation. And I should mention that this, similar to Carrie's data, this was sampled, the soil was sampled in second year corn. So all of that soil had corn for the second year.
Right, so this is a legacy effect again.
Yeah, we're not just looking, or we're not just measuring what that one-time corn crop is doing to the soil. Yep.
Right.
I did an interesting observation off of this chart. Like, at least to me it is. If you look at like continuous corn, so our first column of CC, and you compare it to corn, soy, wheat, and corn, soy, wheat, red clover, they're all the same.
Yeah.
So.
Yeah, there's, yeah. So, yeah, it's starting to show some differences, right? But yeah, in this is one soil health indicator when we look at other ones. But yeah, no statistical difference. So there's quite a bit of variability in that data. We did similar at Ridgetown, and it's following this similar trend. Of course, at Ridgetown, we don't have alfalfa in the rotation. We have continuous soybeans in there. It tends to be the lower. and greater with red clover in the rotation.
Right. So
Yeah,
again,
and so
Corn is a
one
good
of the
thing.
things, so if I could just,
Yeah.
like one of the advantages of Elora and Richtown is that it's very diverse crop rotation, right? A lot of those long-term trials in the Midwest, they just compare continuous corn to soybean corn rotation. And if we just had that, we would say, oh yeah, no differences, right? But because we have more diverse rotations, we are starting to see differences in soil health.
Yeah.
And that relates back to yields. It relates back to what David Hooker and Bill Dean are seeing in terms of resiliency in those moisture stress years, right? Too dry, too wet. They're seeing greater cord yields with red clover in the rotation, with winter wheat in the rotation, that resilience. And as soil scientists, I guess Carrie and I would probably argue, it's soil.
and Dan, like I'm glad you bring that comment up. I'm kind of thinking about, you brought up the comment earlier about it's about feeding the soil and feeding the microbiology, and so what's your kind of thought process behind these different rotations, your rotation that you practice, and your goals in feeding the biology?
I guess it is we see if it's a balance of everything. So we do see a soil life increase just by extending rotations. Like there's anecdotal historical evidence of that happening. So we look at rotations of, the early 1900s. We had multiple small greens, lots of legumes, lots of pasture land, and lots of alfalfa. Economics allowed all of that. So now, as we come into a commoditized world, and we all sell into the same world, corn, soybeans, and wheat reign the world for North America. So now our approach was, how do I maintain how do I build up to those soil levels and soil responses and resiliency that we had back then to now? So we make a conscious effort of putting red clover on every acre, and where we can't, then we add something. I will go planting tomorrow. We see, but it's always balanced against what my economics are. I take whatever I have my corn booked at or my beans booked at this year. That's part of my cost of production, so I can only do so much for like what plants I can put in. Clover always gives me an economic response, even when I ignore the end credit. Like we're averaging 15 to 20 bushel corn gain the following year, which is an astounding number, even at $4.
It is.
So it works. We just have to really push it. The soil health, I'll be right up front, the soil health is not my focus. It's a very important secondary, but it's my economic health that really drives all of these decisions. And
right. And it's
so
trying
we
to
put coverage in soybeans. Yeah.
Right.
So sorry, Ken, go ahead.
And it's trying to marry the two. Like, can you find
Oh, totally.
Yeah.
Totally.
Yeah. Can you find a system where both win?
If I think about it a little bit, like when I sell my soybeans to Bunge or P&H in Hamilton, they don't ask if it came from a soil healthy field. So I don't get offered a premium. When I sell IP beans, I don't get offered a premium if it's a soil healthy field. So it's a matter of like, soil health matters very much, but how do you monetize that? And how do you extract like value? Because that's what the world we operate in. That's what matters.
Right.
So Dan, do you think there could be a future world where you would get a premium for, let's just call it soil sustainable practices?
Yeah, I can dream of one or think of one.
Yeah.
I see so many different soil types, like in Norfolk County, like it's astounding. Soil health will have a different measure. If we have one benchmark of, say, a healthy soil is 80 of whatever unit, but you go into Langton, Ontario or Tillsonburg, they can never get 80 because we're talking about 90% fans.
Yeah.
So, like, how do you make the benchmark even?
Yep.
So part of me wants
Right,
one,
right.
but part of me definitely does not want that.
Yeah,
Yeah,
that's one of the
and I
things.
agree.
Yeah.
I guess I didn't ask about where you were paid for your soil health, right? I asked if a system where if you were adopting soil sustainable practices that you could be rewarded, right? As
you're being
opposed to
rewarded for the
here's your
practices.
soil health level.
Do I want a carrot?
Yeah.
In a way,
Yeah.
like, yeah. How many hours do we have for this discussion? No,
Well,
but I think it'd be great, Laura. Like, I think it needs to be recognized somehow. And the best recognition, because we are all businesses, is somehow like monetary somehow. So if I get like a perpetual cost share, so long as I do something, maybe, I don't know, like, but where does that get funded out of? Like, that's always,
Taxpayer.
yeah. And that's to show like a willingness and a knowledge base amongst the taxpayer to, I don't know, facilitate it and not just jump onto an organic bandwagon.
Yeah.
and so with this conversation about monetizing things, I want to maybe jump into a topic that, Carrie, this is like you recently wrote a review paper on this, and I think it touches on your economic concern, Dan, and this whole question of how do we feed the soil biology. Is a lot of people are talking these days about inoculants. What are the value of inoculants? Are inoculants, like, in an ideal world, inoculants would, boom, they'd improve the soil biology, soil health. In a very ideal world, they would also have an impact on yield, so there would be an economic return to the cost of using inoculants. Carrie, could you talk a little bit about this paper, this review paper that you wrote, and what were some of your findings in looking into the literature?
Yeah, sure. So one of the reasons my group and I kind of put this paper together is because if you're a microbiologist that's worked in like soil plant microbiology, we've been thinking about this for a really long time. Like, are there microbial inoculants that can promote plant growth? And we know that there are organisms that work with plant growth promoting bacteria and fungi that like have a lot of different ways that they can promote plant growth. And so in very recent years, there's been a lot of different companies that have tried to, you know, jump on to find some of these specific organisms and, you know, commercialize them and sell them as an inoculant. And so from my point of view as like a soil microbiologist, I know that there's been a lot of studies for like hundreds of years. People have tried this, and it's tricky to get them to work across the board, basically is what I'll say. You can sometimes get them to work in a greenhouse, but taking them out into the field is a whole different kind of ball game. And so I was talking to my group and I said, we really need to have like a paper out there that really highlights the impact of the soil, like that the soil is actually, the soil environment has a role in this. So if you take the whole soil environment out and you just look at the plant and the microbe, you can find some of these things happening, and that's great. But when you get out into the real world, there's this soil factor that you have to kind of incorporate into your decision making. And that can really drive a lot of things that can make these organisms work or not work when you put them in the field. So that's what kind of the point of the paper was, just to say, hey, we know a lot about soil, and those soil microbes definitely have a role in this, whether these things are going to work. What was interesting is, as we were doing research, there's a lot of work out there looking at microbial inoculants themselves. But there's also kind of a third area of research that is really just saying we should just promote sustainable soil practices, and how does that impact the microbes that are in your soil, and can you be promoting these plant growth promoting organisms just by soil practices. So the two that we focused on were diversifying your plants that are in rotation, either through cover crops, or we looked at a bunch of different ways. So basically diversifying plant inputs. And the second thing was like decreasing your inputs generally is another way. So either decreasing your amount of fertilizer or other types of chemical inputs like herbicide or pesticide. There's a lot of work in that area. So what we kind of found was that a lot of research shows that if you have a diverse microbial community, you will have a tendency to have more organisms that are going to promote plant growth. So you do see kind of the benefit of that.
And the easiest way to get to that, like, do inoculants help you get there quickly, or is diversifying rotations, is that a better bet?
I mean, I think that it depends on your soil and it depends on the year you put them in. I think that there are organisms that people have found that probably you could put in your field and you would get a yield benefit that year. But it's very much dependent on what your microbiology looks like. Like we know there's like a community of microorganisms in that soil that are going to compete with that inoculant like the minute it gets put into the soil. So it's pretty hard to predict how that's going to happen, if they're going to be competitive, the inoculant. And also we know that certain soil conditions will either promote or inhibit those inoculants from surviving and being effective. So there's a lot of things that it's a little bit, I think, scary when you look at the economics of it, depending, like it would be scary for me as a farmer. I don't know how, like what the cost is, but you'd have to see some really good data in a lot of fields, I think, to know that it's worth your money.
Yep.
And Kiri, when you talk about inoculants, this is different than your maybe soybean inoculant that's been on the market for years, decades, or
right. Yeah.
or clover inoculants, or are you talking like bugs in a jug?
I guess there's some pretty standard inoculant, like rhizobium inoculant that you would put on soybean or any kind of legume. Those organisms are very specific. That's a really interesting like symbiosis. So they're basically made to get at those legumes and like to do that interaction. And because it's symbiotic, they need to define a plant to live. And so you have a lot better chance at that interaction taking place with like a rhizobium or anything that's an obligate, like symbiote. I guess what we were thinking about, we actually specifically looked at the other organisms that people are looking at, not rhizobium and not mycorrhiza, because those ones are kind of like these symbiotic. So these are other types of organisms that we know can promote plant growth in many different ways, but kind of taking a look at that interaction.
Dan, you kind of look like you're chomping at the bit there to ask a question.
Well, so I've played with like a lot of the commercially available stuff.
Yeah.
So let's say like comes to mind, everyone will be thinking like Quick Roots. So any of the Novozymes products. Sometimes they work, sometimes they don't. I have found I don't know if it's a correlation yet, but if you have a specific K-mag ratio, they seem to be working better. And I don't know. I've seen some amazing results out of them, but I've seen some really, null results. So like, they don't cover the cost, let alone generate anything. Even sometimes, like, there'll be research that says like soybean rhizobium aren't worth it if you've grown soybeans in the last 1 or 2 years in your rotation. Some of these soils, like the sandier soils, especially because we have less holding capacity for life, it always pays.
Yep.
And even now this year, like I have a trial in my red clover of even like this basic rhizobium versus like inoculated clover versus not, and we'll see what kind of end credit or what happens come next year's crop. But
I'll tell you one
I
thing,
think-
when we do like these trials in the greenhouse, we always do it in a sandy soil.
Okay. Oh, yeah. Well, there you go. Yeah.
Because
Yeah.
you tend to see better responses. You're right.
Yeah.
Like,
Yeah. So you have less background noise that way.
Yeah.
And I know I've had chats with people, and our takeaway sometimes is we can add these bugs in a jug, and we think, you know, it'll say 1.8 billion bacteria per, 100 mil or something, and it sounds huge. But you think you're applying 3 milliliters of this product across an acre. And you think like the population density and the ferocity that's happening in these soils, be it sandy or clay or loam or whatever, like unless they're in for or applied to the seed, they have next to no chance. Like it's you're just throwing somebody downtown who has no idea where they are.
yeah.
Whereas, like with rhizobia and soybeans and legumes, like in alfalfa, like they're on the plant, they know the plant, like the root exudate signals, so they go, boom, that's something I know, and they're on it. And I would assume there's minimal predation on just free living, like on the bacteria themselves from whatever's in there.
Yeah. Yeah, I mean, this paper, it's open access, and like the whole first section was just looking at like microbial inoculants and, really trying to think through like how do we test that and how do we try to select so that they will be more reliable on the field. And there is some really cool research in that area. So it's not that it's, impossible. It's just that I think one of the third things we need to think about is that the soil and how that's interacting. Yeah.
So to wrap this all up, okay, so we've seen these rotations have an impact on some soil health indicators. They have an impact on the soil biology. They've got an impact that soil biology has functions associated with it. And so particularly we were talking about nitrogen cycling, looked at organic matter. How does this all again wrap into crop yields? So Laura, just a final slide. Would love for you to kind of talk about what's happening here.
Great. So this is the similar data that we started the presentation on. So instead of doing it as a bar graph, we plotted soil organic carbon against average corn yields. And forgive me, it's in metric, but so this is the average of 5 years. So 2011 earlier. So we have to keep that in mind. But what we're seeing is the greater your soil organic carbon, there's a good correlation with increasing corn yields. But probably more an indication of what's going on in terms of resiliency is that bottom graph, which is variation in yields. So this is a statistical measure, standard deviation. So over that 5 years, have you had great big swings in your yield because of weather, or has your yield stabilized regardless of your weather? And what we're seeing is lower variations, so lower values when you have more soil organic carbon. So it's protecting from those weather conditions. And
Right.
I think it goes back to soil moisture, soil holding capacity, all the stuff that we know, all the good things that soil organic matter does for our crops in our soil.
Right. So maybe final summary words on that is the message feed the soil, and then and that we're seeing those benefits come back in yield. Obviously, there's an economic conversation to all this as well, Dan, and you're good to point that out. What's some of your final takeaways on that? Why don't we start with Carrie? Do you have a final takeaway from this conversation?
I would say that we need to, I think we need to think about the microbes and think about their role that they're playing in all those things that you want them to do. They can promote plant growth, they can cycle nitrogen, they can cycle those nutrients. And so I think that thinking about diversifying and having a diverse microbial community is probably something that is going to benefit in the long run.
Yeah. Dan, how about you?
Oh, I would second that as well. And it's easier, to do it than when a lot of people give credit for. Grow a small grain. It's a super simple baby step. Minimize your tillage for certain crops that you want to have tillage, but that's slow down, do less. Everything kind of balances out. It really does.
Yep. Laura?
Thanks, Cam. So I would, I guess I agree with those previous closing comments. I guess I'd just like to highlight that it's with the long-term trials and having these side-by-side comparisons that have been in the ground for 25 years at Ridgetown and 40 years at Elora that you really, really see the impact. And especially in a year like we've been having at Ridgetown, like we got hardly any rain in June, and you could see it on the crop. And you wouldn't be able to see that if you didn't have those side-by-side rotation and tillage comparison.
Right. Yep. The value is there. Yeah, it's huge. Great. Well, this has been a fantastic discussion. Thanks again for the three of you joining me. Thanks again to Grain Farmers for hosting us for these two webinars. It's been great. Hope you all have enjoyed it.
Yeah. Thanks,
Great.
Cam.
Thank you. Thanks.
Yep.